Imagine if you wear a grand piano.
Okay, I'm picturing it.
But I don't want you to picture the standard piano sitting in a living room or, the polished Steinway on a concert hall stage.
Right.
Imagine a piano so massive, so impossibly long that it possesses not just the standard 7 1/4 octaves, but a staggering 60 octaves.
Wow. Okay, that's huge.
Yeah, I want you to really try to visualize that. Picture that immense keyboard stretching out before you, just an endless, almost horizon-to-horizon expanse of black and white keys.
Right, like it goes on forever.
Exactly. And those keys represent the entirety of the universe's vibrating energy, every single frequency of radiation that exists.
Okay, I am with you.
Now, here is the mind-bending premise we were starting with today. Imagine that your eyes, the incredibly complex organs you rely on to navigate reality, to appreciate a painting, to recognize the faces of the people you love.
Right, our primary way of experiencing the world.
Right. Imagine that your biological hardware is only capable of seeing a single key on that immense 60-octave keyboard.
It's a deeply unsettling image when you really let it sink in.
It really is.
I mean, the implication is that we are stumbling through a universe overflowing with activity, and we are functionally blind to almost all of it.
Yeah, completely blind.
And, the concept of that 60-octave piano isn't some poetic metaphor drawn up for dramatic effect.
No, it's not.
It represents a precise mathematical reality concerning the extreme, almost comical limits of human perception.
Welcome to the Deep Dive. Today, we are opening up a remarkable historical text that tackles this exact limitation.
It's a fascinating one, too.
We are looking at a compilation of lectures delivered way back in 1909 by a pioneering electrical engineer named Charles Proteus Steinmetz.
Right.
The book is titled Radiation, Light, and Illumination. And let me tell you, when I first started looking through these pages from over a century ago, I expected a dry, dusty engineering manual.
Like a textbook on how to wire a house.
Exactly, a textbook about how to wire a light bulb. But instead, it reads like a philosophical thriller about the nature of reality itself.
Steinmetz was an absolute titan in the early days of electrical engineering. I mean, he was the brilliant mind behind much of the alternating current theory that powers our world today.
Yeah, that guy was a genius.
But in these specific lectures, his goal wasn't just to teach his students the basic math of lighting a room. He wanted to completely deconstruct the true nature of light.
And he really goes all the way back to the basics.
He does. The mission of this text, and I guess the mission of our exploration today, is to figure out how radiation actually travels through the vacuum of space.
Right.
To settle ancient scientific debates about what light even is, and to fundamentally unpack Steinmetz's brilliant framing of the electromagnetic spectrum into those acoustic octaves you just mentioned.
I want you, the listener, to do something with me for a second. Look around the room you are in right now.
Just take a look around.
Yeah, find whatever light source is currently illuminating your space.
Yeah.
Maybe it's a desk lamp, the glow coming through a window, or, the overhead fixture in your ceiling.
Pick one out.
Look directly at that light. We're going to spend this time preparing you for the realization that almost everything coming out of that source, the vast, overwhelming majority of the energy it is violently radiating outward into your room, is completely and utterly invisible to you.
To understand the mechanics of why that is, and to truly grasp the monumental scale of that 60-octave piano, we have to start by tearing down a foundational misconception.
Okay, let's do it.
We have to unlearn a very common myth about how energy travels before we can even begin to talk about the spectrum of light.
Okay, I am ready to unlearn.
Yeah.
Where do we start?
Well, Steinmetz makes a really bold assertion early on in the text.
Yeah, that honestly tripped me up at first.
He states very definitively that radiation is purely a form of energy.
Right. And to explain this, he takes the example of a standard incandescent lamp, which, in 1909 was cutting-edge technology.
Oh, yeah, totally high-tech for the time.
And he breaks it down mechanically. He says you have an electric current. It flows through the resistance of the tiny filament inside the glass bulb.
Right, the friction.
Exactly. That electrical resistance converts the electric current into heat. But here is the part that confused me. He says that heat is then converted into radiation.
Ah, yes.
And I always thought heat and radiation were kind of the same thing.
Our everyday language totally betrays our scientific understanding here. I mean, people use the phrase radiant heat all the time.
Yeah, absolutely.
You sit around a warring campfire, you hold your hands out near a hot radiator, and you say, I can feel the radiant heat.
Sure, it's a completely normal thing to say.
But Steinmetz goes out of his way to point out that this phrase is an oxymoron. It is scientifically wrong.
Wait, really?
Yes. The energy traveling from that campfire to your frozen hands, or for that matter, the energy traveling the 93 million miles from the sun to the surface of the earth, is not heat.
Wait, slow down. If I stand in the sun, I get hot. You're telling me the sun isn't shooting heat at me?
The sun is shooting radiation at you. Heat is a localized state of molecular vibration. It requires matter. Radiation is energy in transit across space. That energy only becomes heat again when it is intercepted by an opaque body.
Like your skin.
Exactly, like your skin, or the asphalt on your driveway, and is actively destroyed as radiation.
Destroyed?
Yes. When the invisible radiation wave smashes into your hand absorbs it, stops the wave dead in its tracks, and that absorbed kinetic energy manifests as the chaotic molecular vibration that your brain interprets as heat.
Okay, let's unpack this. I'm having a really hard time picturing this. Let me try an analogy and you tell me if I'm off base.
Go for it.
Is it like throwing a baseball? If I wind up and throw a fastball as hard as I can directly at your shoulder.
Please don't.
I won't. But if I did, the ball flying through the air isn't pain.
Right.
The ball in the air is just kinetic energy. It's mass in motion.
Yeah.
It only turns into pain, which would be the equivalent of our heat in this scenario, when it is abruptly stopped by your shoulder.
That's a great way to put it.
So the pain doesn't travel through the air. the ball travels.
Yes, the heat doesn't travel through the vacuum of space. The radiation travels.
Exactly. The kinetic energy is the transit mechanism. The pain is the localized result of the energy being absorbed.
Okay, that makes sense.
It's a solid way to visualize it. And what's fascinating here is that applying this framework explains phenomena that otherwise seem completely paradoxical.
Like what?
Consider a pane of glass. Glass is transparent to certain frequencies of radiation. If you interpose a thick sheet of transparent glass between a really hot lamp in your hand, what happens?
I mean, I can still see the light from the lamp through the glass. And if I leave my hand there long enough, my hand still gets warm.
Right. The radiation passes right through the transparent body of the glass. Because the glass does not absorb the radiation, it doesn't destroy it.
Okay.
Therefore, the radiation is not converted into heat within the glass itself. The glass can remain perfectly cold, or at least dramatically cooler than you'd expect.
Wow.
While your hand, the opaque body on the other side that finally stops the radiation, gets hot.
So the energy just ignores the glass. Pretty much. If the energy traveling between the lamp and your hand were actually heat, the glass would have to be heated up to pass it along.
Like a frying pan conducting heat to an egg.
Exactly. But because it is radiation, it just sails right through the atomic structure of the glass without dropping off its energy payload.
That completely reframes how I look at a window on a sunny winter day. The sunlight isn't warming the air between the sun and the earth.
No, space is freezing cold.
Right. The sun is just pitching these invisible fastballs of radiation through a vacuum for 93 million miles, and it only becomes heat when it smashes into the dark upholstery of my car seats.
Steinmetz details a wonderful historical experiment to prove this physical, mechanical nature of radiation. He uses the Crookes Radiometer.
Hold on, is that the little glass bulb with the spinning windmill inside? I've seen those in science museum gift shops.
Yes, that exact thing.
You put them on a windowsill and they spin when the sun hits them. I always assumed the light itself was physically pushing the little sails, like wind pushing a sailboat.
The popular understanding of that little toy is almost always incorrect.
Oh, really?
Yeah. Let's walk through Steinmetz's rigorous description of what is actually happening. The Crookes radiometer consists of 4 extremely light aluminum vanes mounted on a central needlepoint axis.
So it can spin freely.
Right, designed to spin with almost zero friction. These vanes are sealed inside a glass bulb that has been pumped down to a moderately high vacuum.
Meaning there's no air in there.
Well, most, but crucially not all, of the air has been removed. There's a tiny bit left. Now, the defining detail of the apparatus. One side of each aluminum vane is highly polished to a mirror finish.
Okay, super shiny.
And the reverse side of each vane is coated in a flat, dead black material.
Okay, so Steinmetz sets up this spinning windmill to show what happens when radiation hits different types of surfaces.
He brings a source of radiation near the glass bulb. In his 1909 lecture, he uses electrically heated silicon rods, but any strong light or heat source works.
Okay, so the heat's on.
The waves of radiation travel from the rods through the air and straight through the transparent glass bulb. When those radiation waves hit the highly polished, mirror-like side of the aluminum vanes, they are reflected away.
So the shiny side just bounces the fastballs away.
Exactly. Very little energy is absorbed by the shiny metal, but when the radiation hits the blackened side of the vanes...
The black side is opaque to the radiation. It acts like the catcher's mitt in my baseball analogy.
Yes. The blackened side absorbs the radiation, destroying it as a traveling wave and converting it into localized heat.
So it gets hot.
That specific black side of the aluminum vane physically heats up. Now, remember I mentioned there is still a tiny residual bit of air left inside that vacuum tube.
Yeah, you did.
The microscopic layer of gas molecules immediately touching the hot blackened side of the vane also heats up. And what does a gas do when it heats up?
It expands. The gas molecules start bouncing around more violently.
The violently expanding air molecules push off against the blackened side of the vane, creating a tiny mechanical thrust driving it backward.
Oh, I see.
This miniature explosion of gas happens on all 4 vanes simultaneously, but only on the black sides. The whole wheel begins to spin.
Wow.
The brighter or more energetic the radiation source you place near it, the faster the wheel spins. It is a direct, visible demonstration that radiation is a transit vehicle carrying physical energy that can be converted into mechanical work via heat absorption.
That is so deeply satisfying to understand. We aren't watching light push a sail. We are literally watching invisible energy fastballs heat up a microscopic layer of air, creating tiny thermal engines that spin a windmill.
That's a perfect summary.
Okay, so we've established the ground rules.
Yeah.
Radiation is energy in transit, zipping through space until it hits something opaque and turns into heat.
Right.
But if this radiation is a physical thing traveling through space, how on earth did scientists figure out how fast it was going? You can't put a radar gun on a fastball you can't even see.
The quest to measure the velocity of light is one of the most astonishing triumphs of human intellect. Steinmetz walks his students through 2 historical methods, and they both highlight a level of ingenuity that is hard to fathom today.
Yeah, wait.
The first method is astronomical, dating back to 1676 with a Danish astronomer named Ole Rømer, though the refinements continued into the 18th century.
I found this part so incredibly clever. They didn't have lasers. They didn't have atomic clocks or digital sensors.
No, none of that.
They used the solar system itself as a giant cosmic laboratory. They looked at Jupiter.
Specifically, they looked at Jupiter's moons. Jupiter has several large moons orbiting it, and when observed from Earth, these moons regularly pass behind the massive planet, causing an eclipse.
Okay.
Because the orbits of these moons were very well understood thanks to Newton's laws of gravitation, astronomers could calculate the exact minute and second a specific moon, like Io, should disappear behind Jupiter.
And exactly when it should pop back out on the other side.
Right.
They had the train schedule. They knew exactly when the moon was supposed to pull into the station behind the giant gas planet.
The math was solid. But the observations started getting weird.
How so?
They noticed a massive discrepancy. Depending on what time of year they were looking through their telescopes, the moon would sometimes disappear earlier than the calculated schedule, and sometimes it would disappear much later.
And this wasn't just a matter of a few seconds, right?
No, the maximum difference between the earliest observed disappearance and the latest observed disappearance was about 17 minutes.
If I'm an 18th century astronomer, my first thought is that my math is wrong, or my clock is broken.
Natural assumption.
But the delay wasn't random, right? It correlated perfectly with where the Earth was in its own orbit around the sun.
Let's map out the solar system to see why. Picture the sun in the middle of a giant table. Jupiter is way out near the edge of the table, orbiting very slowly. Earth is much closer to the sun in the center, orbiting much faster. Sometimes, Earth and Jupiter are on the exact same side of the sun. They are as close together as they can possibly be in the solar system.
Right.
When the planets are in this specific alignment, the astronomers observed the moon disappearing behind Jupiter at the earliest possible time on their schedule.
Because the light bouncing off Jupiter's moon had the shortest possible physical distance to travel to reach the brass telescopes on Earth.
Exactly. Now, fast forward about 6 months. Earth has zipped halfway around its orbit to the exact opposite side of the sun.
So they're on opposite sides of the table now.
Right. Now, the sun is sitting directly between Earth and Jupiter. The two planets are as far apart as they can possibly be. And in this distant alignment, the disappearance of Jupiter's moon happened at the absolute latest time.
And the delay between the closest observation and the furthest observation is at 17 minutes, which means it took the light an extra 17 minutes to cross the additional distance.
You're doing the math.
Let me try to visualize this. What is that additional distance? It's the entire diameter of the Earth's orbit around the sun.
Yes. The diameter of the Earth orbit was known at the time to be roughly 186,000 miles. So you have a physical distance, 186 million miles.
Okay.
And you have a travel time, 17 1/3 minutes. To make the math simple, 17 1/3 minutes is exactly 1,040 seconds.
I'll trust you on the math there.
Divide 186 million miles by 1,040 seconds, and the result is
186,000 miles per second, the speed of light.
exactly.
Measured centuries ago just by staring at Jupiter and looking at a pocket watch. It completely blows my mind that human beings figured out the speed limit of the universe using such rudimentary tools.
It really is incredible.
But Steinmetz doesn't stop there. He says scientists are rigorous, and they didn't want to rely solely on planetary alignments. They wanted to measure it mechanically here on Earth.
This brings us to the second method Steinmetz describes, which is an incredible feat of 19th century engineering by a French physicist named Hippolyte Fizeau. It's often referred to as the toothed disk experiment.
I need to walk through this slowly, because when I read this section, my brain almost short-circuited.
It's a lot to visualize.
It sounds like a cartoon Rube Goldberg machine for measuring cosmic speeds. Okay, so imagine the setup. You have a very bright, intense lamp. In front of that lamp, you place a spinning metal disc.
Like a wheel.
The outer edge of this disc is perforated with holes. Steinmetz uses the example of 200 holes evenly spaced around the edge, with solid metal teeth in between them, like a giant gear.
If the disk is entirely stationary and one of those holes is lined up with the lamp, a narrow beam of light passes straight through.
Makes sense.
If you rotate the disk slightly so a solid tooth is lined up, the light is blocked.
Got it. Now, you take that beam of light that passes through the hole, and you aim it at a mirror that is located 10 miles away.
Think about the physical logistics of that in the 1800s.
It's absurd. You have to align a beam of light perfectly with a mirror 10 miles across the valley. The light hits the mirror 10 miles out, bounces back, and returns the 10 miles to the spinning disc.
Yep.
You have an eyepiece, or a telescope, set up right next to the lamp, looking through the exact same hole the light just exited.
So the total round trip for the light beam is 20 miles.
Exactly. Now, we start spinning the disc slowly. As it rotates, the continuous beam of light is chopped into discrete flashes. Hole, tooth, flash dark, flash dark.
Right, like a strobe light.
The light goes out through a hole, travels the 20 miles, and by the time it gets back, the disc has barely moved at all. So the returning light passes back through that same hole and into your telescope. You see a flickering light.
But the crucial step is to speed the disc up.
You crank the speed of that disc, faster and faster. Eventually, the disc is spinning so fast that in the microscopic fraction of a second, it takes the light to travel to the mirror and back. The disc is moved exactly half the distance of one hole.
Meaning that when the light returns from its 20-mile journey, instead of finding the open hole it left through, it smacks into the solid metal tooth right next to it.
The light returning from the 10-mile mirror is entirely blocked. If you were looking through the telescope, the mirror completely goes dark.
Right.
The light is blotting itself out because the door it left through has been slammed shut, and the next door hasn't opened yet.
If the engineers knew the exact rotational speed of the disk when the light went dark, they could calculate the speed of light.
Which is already crazy.
But Steinmetz describes taking it one step further for maximum mathematical accuracy. You don't just stop when the telescope goes dark, you keep speeding the spinning disk up even more.
You spin it faster until suddenly the light reappears in the telescope at full brilliance.
Yeah.
What has happened?
Tell me.
The disk is now spinning so incredibly fast that during the 20-mile round trip of the light, the hole it left through has moved away, the solid tooth has passed by, and the next consecutive hole has moved perfectly into position to let the returning light through.
Let's look at the staggering numbers Steinmetz provides for this. To make the returning light hit the next hole perfectly on a 20-mile round trip, a disk with 200 holes must be spinning at exactly 94 revolutions per second.
Wait, slow down. Let me do the mental math. 200 holes on the disk,
Right,
spinning 94 times every single second. That's 200 times 94. That's 18,800 holes passing the telescope every single second.
It is wild.
My brain can't even picture a physical object moving that fast without shattering into shrapnel.
The mechanical precision required to build an apparatus that can survive 94 revolutions per second without destroying itself is astounding. But look at the math it unlocks.
Yep.
18,800 holes pass by per second. Therefore, the time it takes for one hole to move into the exact position of the previous hole is 1 divided by 18,800.
1/18,800th of a second.
And in that tiny fraction of a second, the light traveled 20 miles. If you multiply 20 miles by 18,800, you get 376,000 miles for a full second. But since the round trip was 20 miles, Steinmetz notes that the half-pitch calculation gives the velocity of light as roughly 188,000 miles per second, or roughly 3 times 10 to the 10th centimeters per second.
Oh.
It perfectly validates the astronomical observations of Jupiter, but done entirely with spinning metal and mirrors on a hillside.
It's breathtaking.
Well-
Okay, so they nailed down the speed. They know this energy travels at roughly 186,000 miles per second. But that naturally begs the second massive question.
What is it?
What is it that is moving that fast? What is the vehicle? You mentioned earlier that there was a massive debate about the fundamental nature of light.
The scientific community was deeply divided for a long time. Isaac Newton, arguably the most influential physicist in history, had suggested the corpuscular theory.
Which means what?
He believed light rays consisted of extremely minute material particles thrown off by light-giving bodies with enormous velocities. He pictured it as a kind of high-speed bombardment, a cosmic machine gun firing microscopic pellets of light.
I have to say, Newton's theory makes a lot of intuitive sense to me. If I shine a flashlight at a mirror, the light bounces off at an angle. It feels exactly like throwing a tennis ball against a brick wall. A particle bouncing makes logical sense.
It does make intuitive sense, which is why the theory held on for so long. But another brilliant mathematician, Leonhard Euler, argued for a completely different explanation.
What was his idea?
He believed light was a wave motion, conceptually similar to ripples spreading on a pond or sound waves traveling through the air. Steinmetz explains the definitive proof that finally settled the debate in favor of Euler's wave theory. And that proof is a phenomenon called interference.
Okay, let's unpack this. You need to walk me through interference carefully because the way Steinmetz explains it completely broke my understanding of how light works.
It's a bit counterintuitive.
He says, imagine we want to test Newton's particle theory. If light is a bombardment of tiny bullets, then if you combine 2 beams of light and point them at the exact same spot, they must add to each other. 2 identical beams of light should always create a spot twice as bright. You're just adding more bullets to the target.
The math of particles is simple addition. But if Euler is correct, and light is a wave, then combining 2 beams becomes vastly more complex.
How so?
Think of water waves in a bathtub. If you push water from 2 sides and combine 2 waves, and their peaks align perfectly, what physicists call being in phase, they add together to create a single wave that is twice as high.
But what if they don't align perfectly?
That's the crux of the proof. If the waves are out of phase, specifically, if they're exactly 1/2 wavelength out of phase, the peak of the first wave aligns perfectly with the trough, or the deepest valley of the second wave.
Oh, I see where this is going.
The upward push of the first wave is exactly mathematically canceled out by the downward pull of the second wave. Their resultant force is 0. They blot each other out.
That's crazy.
If light is truly a wave, it should be possible to combine 2 bright beams of light and produce absolute darkness.
Hold on. You're telling me if I cross 2 flashlight beams in a very specific way, they make a dark spot?
Yes.
That makes absolutely no sense. If I add a bucket of water to a bucket of water, I don't get an empty bucket. Adding light to light, making dark sounds like magic, not physics.
It sounds impossible, but Steinmetz details the exact experiment used to prove it, using curved glass plates.
Okay, how does that work?
He says, take a perfectly flat, plain plate of glass. Now take a second glass plate that is very, very slightly curved. Imagine a lens with an enormous, gentle radius, and place it directly on top of the flat plate.
Got it.
Because the top plate is slightly curved, the 2 pieces of glass only actually touch at the very center point. As you move outward from that center point, the microscopic gap of air between the 2 plates gets wider and wider.
Okay, I have my 2 plates of glass with a tiny wedge of air between them.
Now shine a beam of uniform monochromatic light, like a pure yellow light, straight down from the top.
Just yellow light.
Right. When the light hits the curved glass, part of it reflects off the bottom surface of that top plate back up to your eye, but part of the light passes through the microscopic air gap and reflects off the top surface of the flat bottom plate.
So I have 2 distinct reflections bouncing back up at my eye. But the light reflecting off the bottom plate had to travel just a tiny bit further. It had to cross that microscopic air gap twice, once down, once back up.
Precisely. And because the air gap gets wider as you move away from the center where they touch, that extra distance the second beam has to travel is constantly changing.
Okay.
At certain specific points radiating outward, that extra round-trip distance across the air gap is exactly equal to 1 full wavelength of the yellow light. When those 2 reflections combine at your eye, they are perfectly in phase. Peak meets peak. You see a bright yellow ring.
But at other points, just a microscopic fraction of a millimeter further out, the air gap is just wide enough that the extra distance the second beam travels is exactly 1/2 of a wavelength. The second beam is delayed by a half step. When it combines with the first beam bouncing off the top plate, the peak of the first meets the trough of the second. They cancel each other out completely.
And what do you see?
A perfectly dark ring.
Yes.
So surrounding the point where the glass plates touch, you see a bullseye pattern, alternating bright yellow rings and completely dark rings. Bright where the waves add together, dark where they cancel each other out.
Exactly. This phenomenon, interference, is utterly impossible to explain with Newton's particles. Two physical particles cannot merge to become nothing. Only waves can do that. This proved, definitively, that light is a wave motion.
It's so elegant. And what's crazy is that you actually see this in daily life.
You do.
Steinmetz mentions that when you use ordinary white light instead of pure yellow light, things get complicated because white light isn't a single color. It's a mix of all different colors, and each color has a slightly different wavelength.
Right, they don't line up perfectly.
Exactly. Because their wavelengths are different, their dark and bright rings appear at slightly different distances from the center. They overlap and smear together.
And
that overlap is exactly what creates those swirling rainbow interference colors you see on a soap bubble or a thin layer of oil floating on a puddle in a parking lot. It's literally the different waves of colored light mathematically canceling each other out at different microscopic thicknesses of the oil.
It is a beautiful synthesis of abstract math in the physical world we observe. But proving light was a wave raised a massive conceptual problem for scientists in 1909.
What was the problem?
If light is a wave, this raises an incredibly important question. What is waving? Sound is a wave, but it's a wave of something. It's a compression wave of physical air molecules. Ocean ripples are waves of water. A wave is, by definition, a motion. You cannot have motion without a medium to move.
Right. I was thinking about this. If I'm holding a jump rope and I flick my wrist to send a wave down the rope, the wave is the energy traveling, but the physical rope is the medium. If there's no rope, there's no wave.
Exactly.
So since light travels from the sun to the earth through 93 million miles of the cold, empty vacuum of space, what is the jump rope? What is waving?
This conundrum birthed the concept of the ether. Steinmetz explains the logic. Since light clearly passes through a vacuum, since we can pump out all known gases and the light still travels perfectly, the medium cannot be any known gas or matter.
Yeah.
It must be something essentially different, a hypothetical, invisible medium assumed to penetrate all substances and fill all empty space in the universe.
The ether.
Yes. Based on the enormous 186,000 mile per second speed of light, physicists deduced that this ether must possess incredibly high elasticity to snap back that fast and extremely low density so as not to slow down the planets moving through it.
It's fascinating because today, modern physics has largely moved past the mechanical ether with the development of quantum mechanics and Einstein's relativity.
That's true. Physics evolved.
We now understand that electromagnetic fields don't need a physical, mechanical medium in the classical sense to propagate. But in 1909, the ether was the necessary logical bridge. They knew the wave existed, so they had to mathematically define the invisible ocean it was rippling through.
And they were able to define exactly how it rippled, which is equally important for our understanding of the spectrum. Steinmetz distinguishes between two fundamental types of waves, longitudinal and transversal.
Okay, let's unpack these two terms.
A longitudinal wave is like sound. If a bell rings, the sound travels outward to your ear. The physical air molecules vibrating to carry that sound are vibrating back and forth in the exact same direction that the wave itself is traveling. It's a series of compressions and expansions pushing forward.
Like a slinky. If I stretch a slinky out on a table and push one end forward, the metal coils compress, and that visible compression travels down the line. The movement of the metal is parallel to the direction the energy is going.
Perfect analogy. A transversal wave, on the other hand, is like your jump rope analogy. The wave travels horizontally away from you down the length of the rope, but the physical rope itself is moving up and down, perpendicular to the direction the wave is traveling.
So how did they know which one light was? Was it a slinky or a jump rope?
They proved it through a property called polarization. If light were a longitudinal wave, vibrating only forward and backward like the slinky, it would look and behave exactly the same from every angle around its axis.
Because it's just pushing straight forward.
Right. But if it's a transversal wave, vibrating side to side or up and down like the jump rope, it can be physically filtered. Imagine you have that jump rope passing between the vertical slats of a wooden picket fence.
Okay, I'm picturing it.
If you flick your wrist up and down, the wave travels perfectly through the vertical gap between the slats. But if you flick your wrist side to side, creating a horizontal wave, the rope smashes into the wooden slats and the wave is immediately blocked.
Ah. So you can prove light is a transversal wave if you can somehow find a microscopic picket fence for light.
And nature provides them. Steinmetz points to specific crystals, like Iceland spar, which is a transparent form of calcium carbonate.
What does it do?
It exhibits a bizarre property called double refraction. When a beam of normal, unpolarized light, which consists of millions of transversal waves vibrating in all possible perpendicular directions, randomly enters an Iceland spar crystal, the atomic lattice of the crystal acts like a sorting machine.
Oh, wow.
It splits the single beam into two separate rays. One ray contains only the light waves vibrating up and down. The other ray contains only the light waves vibrating side to side. They are polarized at right angles to each other.
So the crystal is basically two picket fences superimposed at 90-degree angles, and it forces the chaotic light to pick a lane.
Exactly.
And if you take one of those split beams, say the vertical up and down one, and try to pass it through a second Iceland spar crystal that you have physically rotated 90 degrees horizontally, it gets completely blocked.
The horizontal picket fence perfectly blocks the vertical wave. This behavior is utterly impossible for a longitudinal slinky wave. It definitively, mechanically proves that radiation is a transversal wave motion.
We actually interact with this exact 1909 science all the time today.
We do.
Yeah. If you own a pair of polarized sunglasses, the lenses are essentially that picket fence. They're designed to block horizontal light waves, the glare bouncing off a flat highway or the ocean while letting the vertical waves through.
That's a great real-world example.
It's why if you wear polarized glasses and tilt your head sideways while looking at your smartphone screen, the screen suddenly goes pitch black. The screen is emitting polarized light and you just turned your picket fence the wrong way.
It's a perfect modern example of the principle Steinmetz was lecturing on. So let's recap where we are because this is the foundation for the core of the book.
Let's do it.
We have established that the light illuminating your room right now is actually a storm of transversal energy waves rippling through the electromagnetic field at 186,000 miles per second and only turning into heat when they smash into something opaque.
That is already a lot to process.
It is. But now we must look at the specific dimensions of those waves, their physical length and their frequency, because this is the transition into the core focus of Steinmetz's text, and frankly, the most profound perspective-altering revelation in the entire deep dive.
The octaves of perception.
Yes. Now that we know what radiation mechanically is, we have to compare our biological eyes to our biological ears.
This is where we bring back the 60-octave piano. Let's look at the actual numbers Steinmetz lays out. He gives the average physical wavelength of visible light as roughly 60 microcentimeters. That is incredibly small. It's about 1/40,000th of an inch long.
And because we know the speed of light is roughly 30 billion centimeters per second, we can calculate the frequency.
The math again.
How many of these tiny 1/40,000th of an inch waves wash over your eyeball every single second? You divide the speed by the wavelength, and the result is a number so large it practically breaks the human brain. The frequency of average visible light is roughly 500 million cycles per second.
500 trillion waves hitting your retina every single second. It's incomprehensible.
It really is.
But Steinmetz realized that comparing vibrations with such wildly different frequencies like sound waves, which vibrate very slowly, and light waves, which vibrate unimaginably fast, requires a specific type of mathematical scale. He turns away from linear math and introduces the acoustic scale. He frames the electromagnetic spectrum using the concept of the octave.
The octave is the most natural way to measure frequencies because it perfectly aligns with how our biology actually processes sensory input. Well, an octave simply means a doubling of frequency. If you sit at a piano and strike middle C, the strings inside vibrate at about 261 cycles per second. If you move your hand exactly one octave to the right to the next C key, that string is vibrating at exactly twice that speed, 522 cycles per second. One octave higher means double the frequency. One octave lower means half the frequency.
And Steinmetz dedicates time to pointing out why this logarithmic scale makes so much more sense for human perception than just counting raw numbers, citing something called Fechner's law.
Yes, Fechner's law.
Fechner's law states that our senses perceive changes based on proportional or percentual shifts, not absolute additive numbers.
This is a crucial biological concept to grasp. Let's use weights as an analogy. If you are holding a 1-pound weight in your hand and I place a second 1-pound weight on top of it, you feel a massive immediate difference. Your physical load just doubled. It's a 100% increase.
Yeah, that would be noticeable.
But if you are holding a heavy 100-pound weight and I add a single 1-pound weight to it, you probably won't even register the change.
True, it would just feel heavy regardless.
The absolute change adding exactly 1 pound is mathematically identical in both scenarios. But your biological sensory system doesn't measure absolute change. It measures proportional change. In the second scenario, adding 1 pound to 100 is only a 1% increase, so it barely registers to your nerves.
And our hearing works exactly the same way. The jump from 100 cycles per second to 200 cycles per second sounds like a huge leap in pitch to our ears. It's a full octave. But the jump from 4,000 cycles to 4,100 cycles, which is the exact same absolute increase of 100 cycles, sounds virtually identical to us.
Exactly, because it's a tiny percentage change.
It's barely a change in pitch because proportionally, it's a tiny fractional shift. That's why the logarithmic octave scale is the perfect ruler for measuring sensory input. It treats every doubling of frequency as an equal step, regardless of how massive the raw numbers get.
So using this perfect biological ruler, the octave, Steinmetz measures the total range of human hearing.
Let's hear the numbers.
The lowest audible sound, the deepest vibrating bass note you can possibly perceive, is about 15 cycles per second. The highest audible sound, the most piercing dog whistle shriek, is around 8,000 cycles per second, though a healthy young ear might hear a bit higher.
Okay.
If you double 15 to get 30, then double 30 to get 60, then double 60 to get 120, and so on, all the way up to 8,000. That covers roughly 9 octaves.
Okay, so going back to our giant imaginary piano, your ears give you access to 9 octaves of reality. That's a very respectable wide spread of sensory input. You get the deep rumbling lows and the sharp sparkling highs.
Right.
Now, Steinmetz applies this exact same proportional ruler to human vision.
This is the big reveal.
Drum roll, please.
The deepest, darkest red light we can see, the absolute lowest frequency of visible radiation before it fades into blackness, is vibrating at about 400 trillion cycles per second.
Okay, 400 trillion.
The highest violet light we can see, the absolute upper limit of our vision on the other end of the rainbow, is vibrating at about 770 trillion cycles per second.
Wait a minute. If an octave is a doubling of frequency, 400 doubled is 800.
The math leads us to a staggering conclusion. The entire spectrum of visible light, from the deepest red, through orange, yellow, green, blue, all the way to the highest violet, every single color of the rainbow, every painting you've ever admired, every sunset you've ever watched, every face you've ever recognized, it all fits into less than one single octave.
It is stunning. It is an existential gut punch. Your ears, which we think of as a secondary sense, can perceive 9 full octaves of vibration. Your eyes, our primary tool for interacting with the universe, can't even perceive a full octave.
It's wild to think about.
Out of all the radiation constantly bouncing around the cosmos, our primary biological hardware is restricted to a fraction of a single octave.
And Steinmetz frames it this way. He mapped out the total known spectrum of electromagnetic radiation at his time. From the longest, slowest electrical waves to the fastest, tightest X-rays. That total known spectrum of radiation covers nearly 60 octaves.
60 octaves. Here's where it gets really interesting. This is where the giant piano metaphor really crystallizes. I want to really build this visual for the listener again.
Go for it.
Imagine that 60-octave piano is sitting in front of you. It is immense. It spans the entire length of a football field. Down at the far left end are the deepest, slowest thrums of alternating current waves. Down at the far right ends are the high-pitched, hyper-energetic screams of X-rays.
Right.
When you listen to the universe with your ears, you can hear a solid 9-octave chunk in the middle. You're playing with two hands. But when you look at the universe with your eyes, your vision is glued to just one tiny, narrow cluster of keys, less than 1 octave wide. Out of a 60-octave cosmic keyboard, our eyes are completely blind to 59 of them.
We live in a universe absolutely overflowing with light, radiating with immense power at every frequency imaginable, and we are practically blind to almost all of it. We confidently think we see the world, but we are only seeing a microscopic, highly curated sliver of reality. Everything else, the vast majority of the universe's energy, is playing in the dark.
It makes you look at a colorful masterpiece in a museum or a vibrant sunset and realize this is beautiful, but it's basically a monotone. You are looking at a masterpiece painted with a single brush hair, while a hurricane of invisible colors is swirling all around you, totally unseen.
Once Steinmetz mapped this out theoretically, he didn't just leave it as abstract math on a chalkboard. He wanted to physically show his students what was happening on those other 59 invisible octaves.
Which is awesome.
Let's walk into Steinmetz's 1909 laboratory and recreate his experiments. How do we explore the frequencies just below and just above our tiny visible octave?
He starts from the bottom, pushing up into the visible octave from below. This is the infrared territory. Steinmetz sets up this demonstration. He takes a pair of rods made of cast silicon.
Okay.
They were substantial pieces of metal about 10 inches long, half an inch in diameter. He hooks them up to a 120-volt electrical circuit with a rheostat, which is a device to manually control the amount of current flowing through. He flips the switch, and electricity starts pushing its way through the resistance of the silicon rods.
As we discussed extensively in the beginning, this electrical resistance acts as friction, converting the electrical energy into intense heat, and that heat is broadcast outward into the room as radiation. But what actually happens to the human observer in the room?
Right.
Steinmetz gradually decreases the resistance, increasing the current. The silicon rods get incredibly hot. If you hold your hand near them, you can feel intense heat radiating off them. If you put that Crookes radiometer near them, the invisible energy bombardment will make the little veins spin furiously.
But if you turn off the overhead lights in the room, the rods are completely invisible. It is pitch black. The rods are screaming out energy. They are radiating massive amounts of physical power into the room. But because the frequency of that radiation is too low, it's vibrating below the 400 trillion cycle threshold of the lowest red key on our piano, your eyes register absolutely nothing. It's a phantom energy.
But then, Steinmetz continues to crank the rheostat, pushing more and more current through the silicon. The temperature rises even higher. As the temperature of the object increases, the total amount of radiation increases. But crucially, the average frequency of the radiation also shifts upward.
So it's getting faster.
Yes, the wavelengths get physically shorter, the vibration gets faster.
They are slowly walking their fingers up the piano keyboard from the left, getting closer and closer to our one visible key.
And finally, the frequency of the radiation breaches the biological threshold of the visible octave. In the pitch-dark room, the invisible hot silicon rods suddenly materialize, glowing a dull, dark red. A tiny fraction of their total radiation is now vibrating fast enough to trigger the chemical receptors in the human eye.
As he keeps pushing the temperature higher, the frequency keeps rising, moving across our little 1-octave window. The glow of the rod shifts from dark red to bright red to orange to yellow. At this point, the silicon is nearing its melting point, so he abandons the rods and switches to a tungsten filament lamp.
Tungsten can withstand vastly higher temperatures without melting. He takes a standard 110-volt tungsten lamp and connects it to a 240-volt circuit. He is pushing it to more than double its intended voltage.
He is absolutely redlining this light bulb.
The temperature of the tungsten filament skyrockets, the frequency of the radiation shifts even higher, bringing in the green, blue, and violet frequencies. When you have all the frequencies of the single visible octave playing together at once, what does your brain see?
You see pure white light. The filament is burning a brilliant, blinding white.
To push the demonstration even further up the octave, to isolate those highest visible frequencies, he switches apparatus entirely to a mercury arc lamp. The mercury arc doesn't rely on simple thermal resistance of a solid wire. Its glowing, electrically charged vapor produces radiation that is naturally concentrated at the highest end of our visible octave.
What does that look like?
The light it casts into the room is a harsh, ghastly, bluish green, containing almost no red or orange wavelengths at all. It is pushing the absolute upper limits of human vision.
Okay, so we've walked from the invisible infrared heat through the visible colors up to the harsh blue-green. But what happens when we push past the visible octave? What is the equivalent of pressing a key on the piano so high that my dog can hear it, but I can't? This takes us into the ultraviolet.
This is where Steinmetz's demonstrations get truly spectacular and a bit eerie. To produce powerful ultraviolet rays, he builds an ultraviolet arc lamp. He uses a condenser discharge between two solid iron terminals. He uses a step-up transformer to hit 10,000 volts, creating a high-frequency electrical oscillation of about 100,000 cycles across the spark gap.
Wait, I need to stop you there to clarify the jargon. He uses a condenser discharge. What exactly is a condenser?
It's the 1909 terminology for what we now call a capacitor. It's an electrical component that stores up a static electrical charge and then releases it all at once very quickly.
Okay, I know what a capacitor is.
So he has this capacitor rapidly charging and discharging, creating a violent 10,000-volt continuous spark between these two iron prongs.
Got it. So there's a 10,000-volt lightning bolt constantly firing in the room. But here is the crazy part that Steinmetz points out. To the naked human eye, this violent 10,000-volt arc produces almost no visible light. It looks like a weak, pathetic little blue spark.
Exactly.
If you hold a piece of white paper under it, the paper's barely illuminated. You'd think a 10,000-volt arc would blind you.
The reason it looks so weak is because almost all of the massive energy being released by that tearing iron arc is vibrating at a frequency much higher than 770 trillion cycles per second. It has crossed over the right edge of our keyboard into the ultraviolet octaves.
So it's out of range.
Yes. The room is flooded with intense, high-energy radiation, but your eyes are completely numb to it.
So how does a professor prove to a room full of students that the energy is actually there if they can't see it? Steinmetz brings in a magic trick. He introduces the concept of a frequency converter.
A very clever trick.
He takes a lump of a natural mineral called willemite, which is a native zinc silicate. In normal room light, willemite is just a dull, greenish-gray, boring-looking rock.
It's just a rock. But watch what happens when he places this dull rock under the seemingly weak iron arc. Suddenly, the willemite flashes into a brilliant, blinding green glare. It glows like radioactive kryptonite from a comic book.
And it's not just reflecting green light from the arc, because we already established the arc isn't producing visible green light. What the rock is actually doing on an atomic level is absorbing those massive, invisible ultraviolet waves.
Right.
As the high-frequency energy passes through the complex crystalline structure of the mineral, it acts as a step-down transformer for light. It takes the invisible high-pitch energy and down-pitches it, slowing the vibration into the single octave of visible green light that our eyes can actually process.
It's the physical process of fluorescence. The willemite crystal acts as a translator, dragging the invisible universe down into our tiny window of perception. And this specific experiment highlights something else that is absolutely wild about these unseen octaves.
What's that?
Exploring them completely shatters our intuitive, everyday understanding of what materials are transparent and what materials are solid.
Yes. This part blew my mind. Steinmetz takes a sheet of ordinary clear window glass, the most transparent thing we interact with in our daily lives, and he slides it between the invisible ultraviolet iron arc and the glowing green willemite rock. Instantly, the rock goes pitch dark.
The glowing green light vanishes instantly, as if a thick lead curtain was drawn over the arc, because to an ultraviolet wave vibrating at those extreme frequencies, ordinary window glass is pitch black. It is completely, utterly opaque. It absorbs the high-frequency radiation and stops it dead.
But then, Steinmetz takes the willemite rocks and puts them inside a hollow tube made of fused quartz. Now, to our human eyes, a quartz tube and a glass tube look pretty much identical. Both look perfectly clear.
Indistinguishable.
But when he puts the quartz tube under the ultraviolet arc, the rocks inside glow bright green again. The ultraviolet light passes right through the solid quartz as if it wasn't even there.
Our entire conceptual definition of transparent is hopelessly biased by our one-octave biological limit. We confidently think glass is clear because it happens to let our specific one octave pass through. We think a brick is opaque because it blocks our one octave.
Exactly.
But if you were an alien with ultraviolet eyes, a glass window would look like a solid black wall, and a quartz crystal would be your clear window pane. It forces you to realize how utterly subjective our experience of the physical world truly is.
We think we see reality, but we only see reality as translated by a very specific, limited antenna. So we've explored the immediate borders, the invisible infrared heat just below us, the invisible ultraviolet just above us. But what about the outer limits of the piano? Steinmetz mapped out 60 octaves. Let's go down to the absolute lowest, deepest notes on the keyboard.
At the far left end of the 60-octave spectrum, we find the electromagnetic fields generated by alternating current electrical circuits. The very power lines running down your street right now are broadcasting radiation. But the frequency is incredibly slow. A standard 60-cycle AC current creates a radiation wave that only completes 60 full cycles every single second.
And since we know from the tooth disk experiment that all radiation travels at the speed of light, 186,000 miles per second, if you only make 60 waves across that entire massive distance, how physically long is one single wave?
Steinmetz does the math for us. If you divide 186,000 miles by 60 cycles, one single wave of 60-cycle AC radiation is 3,100 miles long.
3,100 miles. A single continuous wave stretching roughly from New York City to Los Angeles. You have invisible energy waves the size of the North American continent passing continuously through your body right now, and you feel absolutely nothing because your biology is completely untuned to that slow frequency. It's terrifying and amazing at the same time.
As we move up from those continent-sized AC waves, we enter the realm of wireless telegraphy, what we would now broadly call radio waves. These range from about 10,000 feet long down to about 100 feet long. Then we get to Hertzian waves, which are about 30 centimeters long, used in early spark gap transmitters. And we keep climbing up the keys, octaves upon octaves, until we hit the heat of infrared, then our tiny visible sliver, then the ultraviolet.
And what's sitting at the absolute far right of the keyboard, the highest, most frantic, hyper-energetic frequencies known to science at the time.
X-rays. At the extreme high end of the spectrum, Steinmetz estimates X-ray frequencies at roughly 3 times 10 to the 18th power cycles per second. 3 quintillion cycles per second.
That's a lot of zeros.
The physical wavelengths are infinitesimally small, less than a billionth of a centimeter. At these extreme frequencies, the waves are so densely energetic they don't reflect or refract like normal light. They just blast straight through the soft tissues of your body, only being stopped by the denser calcium matrix in your bones.
So what does this all mean? Bringing this all back down to Earth. What does this all mean for Steinmetz and his engineering students? Why is a professor of electrical engineering spending hours talking about 60 octaves of invisible, continent-sized waves and quintillion cycle X-rays?
Because this massive 60-octave map perfectly frames the illuminating engineer's dilemma. The fundamental job of the lighting engineer is to build a machine, a light bulb, that efficiently produces light.
Right.
But look at the brutal physics of what they are actually trying to do. They are taking raw electrical energy, turning it into heat through resistance, and generating a broad spectrum of radiation. But the human eye only values the tiny fraction of that radiation that falls strictly within that less than 1 octave window of visible light.
Right. If the light bulb produces infrared radiation, your eyes can't see it. It's wasted electrical energy. It's just acting as a very inefficient space heater for the room. If the bulb produces ultraviolet radiation, your eyes can't see it either. Again, completely wasted energy.
When you turn on an early 20th century carbon filament incandescent bulb, the heat causes it to broadcast radiation across many different octaves simultaneously, but perhaps only 1% or 2% of that total radiated energy actually happens to fall into the visible octave.
Only 1 or 2%.
Yeah, the other 98% or 99% is completely invisible heat and ultraviolet noise. From an engineering standpoint, trying to produce light this way is wildly comically inefficient.
It goes perfectly back to the piano analogy. Making an incandescent light bulb is like trying to hit one single specific key in the middle of our 60-octave piano by dropping a giant heavy lead blanket over the entire keyboard.
That's a great way to put it.
Yes, the blanket will successfully press down the one key you want. You will get some visible light, but you are wasting an enormous, absurd amount of muscular energy mashing down all the other 59 octaves of keys at the exact same time, producing a deafening symphony of invisible noise that no one in the room can even perceive.
That is the perfect way to visualize the core engineering challenge. And it's exactly why the entire century-long evolution of lighting technology, from fragile carbon filaments to tungsten to the fluorescent tubes, and eventually to modern highly efficient LEDs, has entirely been a quest to stop dropping the heavy blanket.
Making sense.
Engineers have spent 100 years trying to build precise mechanical and chemical fingers that only strike the keys in that single visible octave without wasting gigawatts of power on the infrared or ultraviolet keys.
Yeah, but there's another tiny detail buried in this section of the text that I found incredibly haunting. When Steinmetz confidently mapped out this 60-octave chart in 1909, he noted that it wasn't completely filled in. He pointed out massive blank spaces in the spectrum.
Yes, there were huge silent gaps where science had not yet detected any specific radiation, but the strict mathematical logic of the octaves dictated that something must be there.
That's so cool.
He noted a vast 4-octave gap between the shortest known electric waves and the longest known infrared waves. He noted an even larger, more mysterious gap between the highest ultraviolet light and the lowest X-rays.
It captures the pure excitement of historical science. Imagine sitting in that lecture hall in 1909, looking at his chalk chart on the board, and knowing that there were entire octaves of the universe just waiting out there to be discovered. Microwaves, gamma rays. They were just literal blank spaces on a chart, mathematically inevitable, but totally physically unperceived by humanity at the time.
It beautifully emphasizes the core philosophy beneath Steinmetz's technical teaching. True knowledge is about realizing the stark limits of our own perception. Once you accept that your biological senses only capture a microscopic fraction of reality, you open your mind to studying the invisible forces that actually shape the universe.
Which brings us to the end of our journey today. What an absolute trip this 1909 text has been. We started by busting the everyday myth of radiant heat, realizing that the sun isn't making space hot. It's throwing invisible fastballs of kinetic energy across the freezing vacuum, waiting to smash into our atmosphere.
We watched astronomers ingeniously measure the speed of those fastballs by tracking the delayed eclipses of Jupiter's moons across the solar system, and we marveled at French engineers mechanically slicing a beam of light into fractions of a second with spinning toothed discs on a hillside.
We proved that light isn't a spray of tiny Newton bullets, but a transversal wave rippling through the electromagnetic field, capable of mathematically canceling itself out into absolute perplexing darkness. And then we arrived at the most humbling realization of all, the sheer narrowness of human vision.
The realization that our eyes, for all their evolutionary complexity, are trapped in a sub-octave sliver of a 60-octave universe. We explored the invisible infrared heat pouring off the silicon rods, and we used glowing willemite crystals to drag the invisible ultraviolet arc down into our tiny, limited visual window.
The next time you walk into a room and flip on a light switch, I want you to really look at that bulb. Appreciate the intense, century-long engineering struggle required to efficiently hit that one visible note. But more importantly, I want you to look at the space around it and think about the 59 octaves of energy pouring through that room that you aren't seeing.
Think about the 3,100-mile-long AC waves from the neighborhood power grid washing over you, completely unfelt. Think about the high-frequency UV radiation bouncing off the window glass that looks perfectly clear to you, but is acting as a solid black wall to the universe.
We live inside a deafening, blinding symphony of radiation, and we are only experiencing it through a tiny keyhole. Steinmetz pointed out massive blank spaces in the spectrum back in 1909. And while we have filled many of them in with our modern technology, it leaves you with a lingering, almost spooky question. Considering that your body's completely numb to the massive continent-sized radio waves passing through your living room right now and blind to the UV waves crashing into your skin, what other unseen, unfelt frequencies might be playing in the universe's remaining blank spaces right this very second? Frequencies we haven't even built the math or the machines to imagine yet. The 60-octave piano is playing a masterpiece. We just have to figure out how to hear it. Thank you for joining us on this deep dive.